my chemistry friends. Thank you to one of your classmates for making that video. If you can figure out who it is, bonus points. Just kidding. But I will be offering some sort of extra credit for students who make little introductions to those for my Edpuzzles moving forward, just to make something a little bit exciting. I'll post more information about that later, but if you feel like that'd be something fun, I'd greatly appreciate it. So welcome to Unit 8. We're going to be talking about acids and bases. There's a third thing in this unit that we'll be talking a lot about, but we'll learn about that later. And in your last lesson, you did a bunch of preview questions about acids and bases, and I was able to see that a bunch of you already know a lot about acids and bases, or that you were able to kind of use the images and the kind of reference table materials I gave you to figure a lot of it out on your own. So we're going to move pretty quickly through the basics. Today's lesson is going to be all about the definition of what an acid and a base is, and we're going to be looking at pH. pH is something that hopefully you've done previous lab experiments with, and so unfortunately we're not going to be able to do this in person, and this isn't very common household object eLab. So I have a simulator, which you may have looked at on Monday or Tuesday, that's going to let you explore some things about acids and bases. Okay, so here's kind of overview right now of our Unit 8. It may change, but I expect it to be done in about 2 to 3 weeks. So our learning target for today, I can identify a substance as an acid or a base based on testing pH with various indicators. If you don't know what those words mean, we'll talk about them here today. And lastly, we want to be able to define the terms Arrhenius acid and Arrhenius base. Okay. So today you already did your warm-up, you're working on your Edpuzzle, you have a lab activity to do today. Remember, labs count as minor assessments, and so it's a very nice way to boost your grade by doing a good job on those, and then you will have an exit ticket at the end. So here we have on your warm-up, I asked you what comes to your brain when you think of the word acid, and here's a word cloud that I made based on kind of the common responses. As you see here, we have burning liquid, okay? That is a huge kind of idea of what acids are in the real world, and you're not entirely wrong. We'll talk more about what that means today. I see the word so dangerous, burning skin, metal, corrosion, pH showed up a lot. That's excellent. That showed me you guys learned a lot of those things. Reaction, toxic, lime, lemon juice, things like that, okay? So a lot of you have some real world ideas of what acids are, at least those of you who filled this out. If not, hopefully you've experienced them a little bit before, and you've probably ingested some acids today at some point, okay? So this is the list of common acids that you were given on your reference table. We have hydrochloric acid, nitrous acid, nitric acid, sulfuric acid, sulfuric acid, yada yada, cool, cool, cool. Okay, and the question was, what do these all have in common? And the answer is what makes them Arrhenius acids. So if you look closely at all of these, yes, they all end in the word acid. That's just part of the rules of naming acids. Yes, they all end with AQ, meaning aqueous or dissolved in water. Most acidic and basic substances, they function best as aqueous solutions, meaning they're not going to really do anything until they're dissolved in water. And so that's not what makes something an acid, but if you look at the front of the chemical equation, they all start with the letter H, meaning they all contain hydrogen. Okay, and so Arrhenius acids are focused just on that beginning H symbol. Okay, and so an Arrhenius acid, Arrhenius is some dude who studied acids and bases and realized these things, so that's what this is named after. Arrhenius acids are officially defined as substances that produce H plus ions as the only positive ion in solution. And when it says in solution, it means dissolved in water. Okay? H plus ions more commonly are referred to as hydronium ions when you're talking about acidic substances, and that's because when you take an H plus, dissolve it in water, you get H3O plus, okay? Hydronium is a polyatomic ion. It's located on table E. I actually think it's the very first one listed. And so if you have H plus ion in solutions, it's the same thing as saying you have H3O plus, okay? And so when we're talking about acids and bases, acids are going to have this H plus. If there's no H plus, then it's not going to be defined as an Arrhenius acid. Okay. Now, acids are stronger and weaker, okay? Some acids, like lemon juice, you put on your food and you ingest and you're fine. Other acids, like battery acid, you don't want to ingest that because it's not going to work out, okay? And it has to do with the relative strength of the acid. And so when we say a stronger acid, we mean more ions will dissociate in water. So if I take something like HCl and dissolve it in water, I will get a lot of H plus ions and a lot of Cl minus, but those don't really matter. The one is the H plus ion. This is what makes it a strong acid. The more H plus you have, the stronger your acid will be. Okay, defining characteristics. Acids often have a sour taste. Okay, if you have stronger acids, they can burn through your skin and clothing. So if we were doing this lab in person, we'd be wearing lab aprons. And characteristic of acids that we've already seen in our labs is that they react with metals. If you remember, we did this reaction in our metals lab. We did it when we were learning the signs of a chemical reaction. If I take something like hydrochloric acid, mix it with magnesium, you're going to see bubble, 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 fizzy, fizzy, fizzy. That is a characteristic of most acids. They will react with metals. We'll talk about the ability of metals to react in our next unit. Okay, and as you saw, most common acids are listed on table K. So if you were taking the regions, which of the following is an arrhenius acid, you would always go look at table K first. Okay, so here's just a visual to kind of represent strong versus weak acids. Weak acids, for a variety of reasons, the strength of their bond, for example, hydrogen and fluorine is an extremely strong covalent bond. That is not going to separate, and so hydrofluoric acid is a very weak acid. So you're going to get very few of these H plus ions. But something like hydrochloric acid, very, very strong acid, when you put it in water, most of it's going to dissociate, meaning the ions are going to separate, and you will have a lot of those H plus ions. If you want to learn more about the relative strength of acids and bases, I highly recommend playing the collisions game for acids and bases. This one doesn't so much focus on the Arrhenius definitions, which is what the regions focuses on, but if you want to explore that, I highly recommend it. It's very informative, okay? So with acids, most people know what acids are, and they also know that they're often paired with their partner, which are bases, okay? And so here is your word cloud that generated from the warm-up about what you think of when you hear the word base, okay? The most common word was base and pH. And most people don't know much about bases other than they're the opposite of acids, and so that's why the word acid, I'm not surprised to see, is big on here as well. So we see chemicals, alkaline, very good vocab word, baking soda, cleaning products, soap, home. A lot of people were thinking base like your home base or a military base, things like that. Not really related, but it's okay if you put it there. So a lot of people don't know much about bases other than they're the opposite of acids. And if we look at our table L on a reference table, this is a list of common bases that the regents would talk about. There's one on here that's an outlier, and it's ammonia, so I'm going to cross that one out for right now. And if you look at the other three, the thing that they have in common is what is defined as an Arrhenius base. And so if you notice, they all have an OH in the chemical formula, and they all have hydroxide in the name. Hydroxide is a polyatomic ion as well. It is OH with a negative charge. It is also located on table E in your reference table. And so the dude Arrhenius, who was exploring acids and bases, he realized that the things that behaved similar all had hydroxide in them, and so that's what he defined as a Arrhenius base. So Arrhenius base is something that produces OH ions, is the only negative ion in solution. This is going to be a hydroxide ion dissolved in water. Very important, if you have a covalently bonded OH, that's actually an alcohol group, which we'll learn about when we talk about organic chemistry, and it's not the same thing. Okay, you will know it's different because the OH will be bonded to a metal, and an OH that's covalently bonded in alcohol will typically be bonded to carbon. And so similarly with acids, the stronger the base, that means the more hydroxide ions you have. So the more of this OH, the stronger your base is going to be. Okay, now I do not recommend this, but bases, weak bases such as soap, have a very bitter taste. And so the thing that you consume more often is an acid. And bases, you're not going to eat them. If you've ever accidentally got shampoo in your mouth in the shower, or you accidentally ate soap, because that's what you do for fun, you'll notice it doesn't taste very good, and that's because bases all kind of have that characteristic bitter flavor. Just like acids, they can burn through skin and cloth. They actually are more dangerous than acids because if you take a base and put it on a lipid, which hopefully you know you are made of lipids, the organic fats in your skin, a very strong base will actually break down fats and turn you into soap. And so there's a scene in Fight Club or something, I've never seen it, but that's how they used to make soap back in the olden days. They'd use lye, and animal fats, and it will dissolve it, break it down, decompose it, and turn it into soap. So when you're talking with bases, they're actually way more dangerous than acids. Acids are still obviously very dangerous, but bases as a whole are more dangerous to us as human beings for various reasons. So on your table L, you saw the most common bases. They have hydroxide. We'll learn about why ammonia is on there later on. It's a different definition of what makes something an acid or a base. So here is kind of an overview. If you have an acid and it dissolves in water, you'll get an ion and H plus ion. You're looking for those H pluses to tell you that something's an acid. If you have OH minuses, you're looking for something to be a base. Okay, so that is overall the definition. Arrhenius acids contain H plus ions in solution. Arrhenius bases contain hydroxide ions in solution. So I have a question for you. The most common substance that we talk about is very important when we're talking about acids and bases, and that is water. So looking at water, what do we notice? So hopefully you notice that water is essentially a hydroxide ion from a base bonded with a hydrogen ion from an acid. And so water is like this kind of magical substance that we talk a lot about in this class. And one of the key things is that water is what is called amphoteric. Amphoteric means something that can behave like an acid or a base. It really just depends on who it's working with, what other substance is there in the water. It will make more sense when we learn the other definition. But because water is kind of an acid ion bonded with a base ion, it's both an acid and a base, but neither an acid nor a base. So when we're talking about acids and bases, it's important to remember that there is a third category. Water falls into that third category. Water's special in that it's amphoteric, but ultimately water is neutral. It's neither an acid nor a base because it can be either an acid or a base. So for your lab today, you are going to be looking at real-world substances virtually and identifying them as acids, bases, or that third category, neutral. Okay, the key things is you want to remember some things about acids and bases. You guys saw a bunch of things about indicators on your warm-up. A lot of you figured out what this lovely little rainbow scale is. Here's some answers from the warm-up. I don't know its name, but it basically works to detect whether a liquid is acidic or a base. The red indicates an acid, the blue means that it's a base. Okay, it's the pH scale, how basic or acidic something is. 1 is the most acidic, 14 is the most basic. So a lot of us remembered this pH scale, okay? And if you look right here, 7 means it is neutral. Now, there are several indicators. There is pH paper, which we'll use this yellow paper, which we would have used in class, that will give you the rainbow scale. But then there's also litmus paper here. A lot of us did this correctly, okay? So when you're using litmus paper, you actually want to use both colors, because if they don't change, then that could mean that it's the opposite, or it could mean that it's neutral. Okay, so for example, we're going to test our little friend lemon juice right here. I have a piece of red litmus paper, and when I open this and put the litmus paper in, you will see that there is no color change, okay? However, you cannot automatically assume that this means that this is a base. You want to make sure that you test both colors of paper, because now that the blue paper has turned red, you can use that to help you remember that this is an acid. If neither paper changed color, for example, if I did this in water, if neither paper changed, you would know that it is neutral. When you're using litmus paper, the easiest way to remember is that if it turns blue, it is a base. Okay, so if I take red paper and put it into a liquid and it turns blue, it is a base. And if neither paper changes, then you have a neutral substance. Okay, Down here is the pH scale. A lot of you remember this correctly. 0 to 14 is what pH is counted by. We'll learn what that means in our next lesson. 7 right in the middle means neutral. So pure water is always going to have a pH of 7 because it's perfectly right in the middle. Acids are going to have low pHs. Bases are going to have high pHs. A way that I remember that, A comes before B in the alphabet, so acids are the first group of numbers and bases are the second group of numbers. Okay, so in your lab today, you're going to be exploring pH. You're going to have kind of this virtual simulator here. When you go here, you're going to have macro, micro, and my solution. You're going to have the opportunity to explore most of these, but basically what you do is you click the little syringe and you will fill up your substance, and then you drag this little green dude and it will tell you what your pH is. So we said water is neutral, it should have a perfect pH of 7. If you click in the micro, it's going to start to show you what the actual H3O to O minus ratio is, but what I think is more helpful are these numbers here on this side. The red is showing you the hydronium or the acidic content, and the blue is a base, okay? And so if the blue is higher, you're going to know you have a more basic substance, and if the red is higher, you're going to know you're going to have a more acidic substance. Okay, so that is what I have for you guys today. As you finish your Edpuzzle, you're going to move on to do your lab. I will have the links in Google Classroom, but they will also be linked in the actual lab document itself. If you're taking AP tests over the next couple of weeks, good luck studying. You're going to do great. If you need anything, please let me know. But otherwise, that's it. Have a good day.